Welcome to lecture number 3. And so remember, when we have a robot, what we want to be able to do is talk about where the position of every part of that robot is. And so typically we'll put a coordinate frame somewhere on the body, and then we want to know, well, what happens as I move this joint? And as I move this joint, how does that change the coordinate frame here? And how does that propagate all the way out to the hand? And so today we're going to learn the important step of how we represent not only rotations from one coordinate frame to another, but also how we can compose those rotations from one joint to the next, and also how we talk about how the coordinate frame itself is positioned in 3D space. So let's get ready. Let's start with a review. If somebody talks about a coordinate frame, they are talking about both an origin and 3 mutually orthogonal vectors, because we're going to talk about where is the x, y, and z. And these are a little bit more than that because we're also excluding everything that's left hand. So we only care about the right hand rule basis vectors. And since they're basis, that means that they're unit vectors. We know that they're orthogonal. And this right-hand rule, that means that the determinant is going to be equal to 1 and not -1. Left-handed will be negative. So when you have this coordinate frame, we're asking for, tell me where the origin is, tell me where x is, tell me where y is, and tell me where z is. And so these little numbers over here is the identifier. Now the rotation matrix is just those 3 more mutually orthogonal, again, right-hand rule, basis vectors, and that's all we want. And so we're going to get some R matrix, where this is the item, and this right here is the coordinate frame that we're referring it to. And then there's going to be 3 entries. There's just going to be x. I'm talking about x1 in frame 0. I'm talking about y1 in frame 0 and z1 in frame 0. Just to remind ourselves, this p1, that's talking about, and this should really be p superscript 1. So what p1 is, it's the coordinates of p in frame 1. And so you write frame 1 as O1, X1, Y1, and Z1. Whereas P in frame 0, the superscript, we're talking about the coordinates of P in frame 0. So that's going to be in frame O0, X0, Y0, Z0. Now, before we go any farther, we're going to need a handy shorthand because it'll take us forever if we write down these cosines. So if I'm talking about cosine of theta in this course, I'm going to write it as C subscript theta. If I'm talking about something like sine alpha, we'll just write S subscript alpha, and then we will know from context that we are taking the sine of alpha, or whatever the subscript is. So now it's time to talk about these basic rotation matrices that are about one axis of the coordinate frame, because from these we can build many other matrices. This first one, we want to know what coordinate frame are we rotating around. Well, notice we've got a 1 right here. And since we've got this 1 over here in this x frame, remember this frame right here, this is x something in our new frame. So we'll just give it in frame number. And we're saying, well, it's the same as the basis frame. So we are rotating around the x. We've seen this before. So x stays the same. And so all our rotation is in y and z. So they've got no components in the x that are changing. And so this is the same thing that we've seen before. This is the cosine of theta minus sine of theta, and then cosine of theta. The next one we have, again, this one, the y basis frame is not changing, so we're rotating around that. In order to figure what these are, we just take this entire matrix that we had here, and we're going to shift it 1 to the right, and we're going to shift it down. All the entries are going to rotate. So this cosine was going to shift over to this side and then roll over to the top. And so we get a cosine, but this time it's of theta. This negative sign that we had, it's going to rotate 1 down. It's going to rotate 1 over the side and then shift down. So we get our negative sine of phi. I've already got a cosine of phi up here. And then our other entries proceed in the same way. Sine of phi and cosine of phi. And then finally, this one over here, you can see that we're rotating around the z-axis. This is rz of psi. It's easier to see that this one over here is just rotating diagonally up this way. And so we can shift all these entries. This is cosine of psi, negative sine of psi, sine of psi, and cosine of psi. And so we call these 3 entries, these are our basic rotation matrices around x, y, and zeta. From these, we can construct any other rotation in the world. So now it's time to talk about rotational transforms. And so often we've got some rigid object that has a coordinate frame attached. And that coordinate frame, we're going to call that frame 1. And that's moved somewhere, and then we want to see what is that point in a different coordinate frame. In this case, how do we go from P1 into P0? And so I've illustrated this with different colors here because P1 is some UVW that's in frame 1, and we want to figure out what is that same coordinate in frame 0. So I'm going to animate those once because that's just beautiful. And so we've got this coordinate of P is given by a UVW, and we want to know what is that value in frame 0. So we have to make that conversion. So we're going to switch into Notepad for that. So again, we are given P in frame 1, which is a collection of the distances in x1, y1, and z1. What we want to know is what is P in frame 0. And so it helps to remember the definition. P in frame 0 is just P1 dotted with x0 and P1 projected on y0 and P1 that is projected on z0. So P1 we have as our definition, and these beautifully colored, this UVW is dotted with x0. So we can do that same thing through here. It's also ux1 plus vy1 projected on a y0, and the same thing. And then now we can take that and we can apply the distributive rule to that. So this is ux1 dot y0. And continue that for our z-coordinate. And now what we can do is we can factor out our u, our v, and our w from this term. Let's circle those. We've got our u's here. And so we have our u, first case, it's times x1, xo. This u is also times x1 dot yo. It helps if I just show my divisions in here. y1 dot yo and our y1 dot zo. And then finally we've got our z1. See this term here, it's right there. So we factor that out. When we look at this beautiful matrix that we've constructed, this is merely the rotation matrix, which is R. If you look at this, this is what is x1 in frame 0. This is y1 in frame 0. This is the basis vector z1 in frame 0. So this is really just rotation matrix 1 in frame 0. And thus, what we had over here, P0 is equal to R10, and this term right over here is P1. Remember, UVW is how you find P in frame 1. And so P0 is just a rotation matrix times P1. What we're going to have here is 3 interpretations of a rotation matrix. The first one that we have is that a rotation matrix, which you just saw here, is a coordinate transformation of the coordinates of a point 2 in 2 different frames. So if you want a picture of this, you can sketch this out yourself. We've got a coordinate frame here. We've got some gorgeous point P. And we want to be able to refer to its coordinates in 2 different frames. There's only so many frames I can draw myself. So these are the 3D frames I can give. What we're saying is we're taking this point and we want to project it into this frame. Whereas in this other frame, I'm projecting it down some quantity here. So I'm projecting that point P into 2 different frames. Another way that we can look at a rotation matrix is it's taking the orientation of a transformed coordinate frame with respect to a fixed coordinate frame. So we can think of this as I'm taking some big matrix R is going from some new frame with respect to that fixed frame 0. So what is the orientation of this transformed coordinate frame with respect to the fixed coordinate frame? And our third way to think about a rotation matrix as it's an operator that takes a vector and rotates it to give a new vector in the same coordinate frame. And we'll use this in robotics because we want to move some vector. So I've got some fixed coordinate frame, and I've got some vector v. Maybe what I want to do then is take that vector and rotate it to a new position. And so this rotation matrix gives me a way to give an operator that rotates it. So here's an example of definition number 2. We've got a fixed frame, and we want to talk about the orientation of a transformed coordinate frame. So over here, I've got this point PA, and I'm going to rotate it by pi about the z-axis. So I'm going to call this rotation that I'm applying R1 in frame 0. It's a rotation of pi about the z-axis. Now we could go back up to our definition of a rotation matrices to figure this out, but we can also just reason this directly out. So that's the way we're going to do it right now. So we know this rotation around z, so that means that this column is just going to be 1, so there's no component of z change in x or y either. So we can fill those in as well. Now if you look at it, if you think about, I'm going to rotate, this is my x, my y, and my z all in frame 0. Then I'm going to rotate by pi. That means that now my x is going to be pointing out here, my y will be pointing out here, and my z1 is going to be pointed there. And so all that's happened is x has changed directions, so it'll be a -1, 0, and my y has changed directions, 0 and -1. And so my orientation, where is PB? This is right here. PB right here. That is just a revolution of r of z pi, point B that was in frame 1. Or we can say it's just a revolution of z pi of PA that's in frame 0. See, this is PB in frame 1, rotation of pi about that. Okay, now let's look at our definition number 3, which is an operator that takes a vector and rotates it to give a new vector. V superscript is equal to 0, 1, 1. This t over here means I'm going to take the transpose of it. And so here we've got a picture here where we're taking this v, it's rotating by theta around here. That is a 90-degree revolution, pi over 2, and we're rotating it about this y0 axis by pi over 2. So we want to know, what is v1 in frame 0? Well, that revolution that we did, we said we were going to do a revolution about y by pi over 2 times our original vector. So we can write our original vector in 0, 1, 1. We're rotating about y, so I can put 1, 0, 0, 0. Then this is a y of pi over 2. We think about what happens if we rotate by pi over 2. This z1 is now going to be pointing in this direction. My x, this direction. So my x is now going to be in my negative z. And my z is in my positive x. And so now I can take multiplying this by this. I get a 1, and a 0 as my output. And there's my answer. So the next thing we're going to talk about is called a similarity transform. And what we're really talking about is how do we apply some transformation A in frame 0 if we're currently in frame 1. So we're going to talk about similarity transforms. We'd like to be able to apply the same operator in different coordinate frames. And so to make this a little bit easier to understand, I have drawn here a teapot. This is the famous Utah teapot. And over here you see that I've put in red and in blue 2 different coordinate frames. And so it's the same teapot, it's just in 2 different coordinate frames. And so if you're in world 0, then you're looking at this with the x coming towards your right. Now it's just as valid if you're in frame 1, you would always also put so this is in blue, you'd also put x1 to the right. And so this teapot is flipped by 90 degrees in these two. It's the same teapot, so I'm just showing it from 2 different points of view. Now imagine that we want to apply a scaling transformation. So that's written in A over there, so this is 4 by 4 matrix. And we want to know, how do we apply that to all the points in the teapot? If you normally apply it, if this is an A is made for frame 1, then you just multiply it times every point, and you'll get this transformation applied. But if we were to multiply A times the teapot in frame 1, then it's going to do different things than if it was in frame 0. You'll notice that this is extending it twice as far along the x-axis, and it is shrinking it along the z-axis. So you can see here is the effect of this scaling transform. And so it is stretched it along the x0 axis. But if you notice, that is the negative y-axis in frame 1. And so we can't just multiply A times our points in frame 1. We have a problem. And so what we need to do is come up with some transformation B, which stretches it by a factor of 2 in the y-axis. The similarity transform teaches us how to do that. So the trick of this similarity transform, to apply this transformation A in frame 0, if you happen to be in frame 1, is to first switch into that frame. This is very much like the Laplace transform. Remember, in the Laplace transform, there were certain problems that were much easier to solve in the Laplace domain than the time domain. So what you did with the time domain problem is first you switch to Laplace, and then you do operation, which was easier there, and then you did your inverse Laplace to get back. And so that's what we're going to do. So we're first going to switch in coordinate frame 0, then we're going to apply A, and then we're going to switch back to frame 1. This only works if A is a matrix representation of a linear transform. In O0, x0, y0, z0, and B is the same linear transform in O1, x1, y1, z1, then we can say that A and B are related. As B is, we're going to do a rotation from frame 1 and frame 0. I'm going to invert that. So now I am in frame 0, apply my A, and then I'm going to transform back. And so if we think about this term right here is really just R10 transpose A R10. And that's true if this is the rotation matrix. to get us into frame 0, we apply A, and then we switch back to frame 1. Let's do an example of a similarity transform. So let's say that we've got two coordinate frames, 0 and 1, and they're related by this R1 in frame 0. A is our z theta relative to the frame 0, relative to frame 1. And what we're going to need to do is write in this is B, 1, 0 inverse A, and R1, 0. Transpose, we've already got, we'll just have to take the inverse of that. So that's 0, 0, 1, 0, 1, 0, negative 1, 0, 0. We want to take the inverse of that. And then my A is a rotation z about the z-axis by theta. So we know that. That's c subscript theta, negative s theta, sine of theta, cosine of theta. And 0, 0, 1, 0, 0. So that's my 8. And then I need to transform it back into frame 1. 0, 0, 1, 0, 1, 0, negative 1, 0, 0. So the first thing that I'm going to do is apply my inverse to here. Remember, that's just going to be the transpose. So I can handle that myself. 0, 0, negative 1, 0, 1, 0, and then this negative 1 is transposed with the 1, 1, 0, 0. And then let's do our multiplication here. And so we've got this term times here. So we get a 0 negative sine theta and a cosine of theta. We're going to take this row and multiply that through, and we get a 0 and a cosine theta and a sine theta. And then this term comes through and we get a negative 1. And nothing else. And so finally, b is equal to, I'll do this to here, negative 1 times 1 is a 1. And then we get 0, 0. Now I've got this term here with a 1, so I'm going to pull out the 0 cosine of theta, sine of theta, and I've got a 1 coming through here. So I get a 0 negative sine of theta, cosine of theta. And then I have my transformation. It's now time to talk about composing rotations. So if I've got a frame 0 and a frame 1, those are related by a rotation of what is 1 in frame 0. Whereas 0 and 2 are related, what is 2 in frame 0. We'd like to know what is 1 in frame 2 or 2 in frame 1. These are something that's missing so far, but we can figure that out. Just a little bit of algebra. So if I've got p in frame 1 and I want to know what is p in frame 0, well, what is frame 0? Frame 1 and frame 0 is given by R1 in frame 0. Similarly, if I want to know P2 and P1, well, what is the frame 2 in frame 1? Similarly, if I want to know what is P in frame 0 and P in frame 2, well, that's just R2 in frame 0. P0, this R2 in frame 0, I could say, well, it's just a rotation of 2 and 1, rotation of 1 in frame 0. Another way that you could see this, when we get this, P0 is equal to R10 in frame P1. And then I said that P1 says R10, R21 in P2. And so thus, this rotation R2 in frame 0 is equivalently represented by multiplying these two together. And so this is a composition of two rotations to get this total transformation, which is very handy if I've got a frame here and I want to figure out, well, how do I get into frame, my next frame along here, if I get some total transformation from 1 to 2 to 3.